Welcome back, fellow fractal explorers. In our journey so far, we've encountered stunning examples of fractals throughout the natural world, from coastlines to broccoli. We saw how life leverages self-similar scaling for vital functions. Today we're going to dive deeper into the mathematical techniques used to intentionally construct fractal geometry. By recursively applying simple rules, we can build fractal shapes with infinite complexity from the ground up. We'll look at classic fractals like the Cantor set, Koch snowflake, Sierpinski triangle, and Mandelbrot-Julia sets. We'll see how recursion and feedback are key to generating fractals through repeating transformations. These mathematical fractals provide pure realizations of the repetitive symmetry that makes fractals so endlessly captivating. They show how fractal dimensions describe the infinite detail between whole number dimensions. Understanding these construction methods gives us tools to engineer and analyze fractal systems. So let's delve into the abstract fractal factory and see how mathematics manifests infinity. The Cantor set is a classic one-dimensional fractal mathematical construction invented by Georg Cantor in the late 1800s. It starts with a line segment. Then you remove the middle third, leaving 2 segments. Next, you remove the middle third of those, leaving 4 segments. By repeating this process infinitely, you get the Cantor set. This fractal dust of points has several special properties. It is uncountable, meaning the number of points cannot be mapped to the natural numbers. It is also a space-filling curve. The points perfectly fill the one space, despite the total length shrinking to 0. The Cantor set maintains a topological dimension of 1, but its Hausdorff dimension describing its fractional complexity is approximately 0.63. The Cantor set illustrates how fractals can remove area yet maintain topological features, like connectivity. This mind-bending math laid early groundwork for fractal geometry. Another pioneered mathematical fractal is the Koch snowflake, invented by Swedish mathematician Helge von Koch in 1904. It starts with an equilateral triangle. Then you divide each line segment into thirds and replace the middle third with 2 new segments forming a bump. This creates a 12-sided star. When you repeat this subdivision and replacement process infinitely, you get the Koch snowflake with its iconic jagged, snowflake-like shape. The Koch snowflake has several interesting properties. As you iterate further, the perimeter length approaches infinity, while the area remains finite. It exhibits exact self-similarity. Any subsection is an exact scaled-down replica, and it has a fractional dimension of approximately 1.6. The Koch snowflake demonstrates how simple recursion can quickly build geometric complexity, foreshadowing the beauty of fractal structures. The Sierpinski triangle is another famous example of a recursive mathematical fractal. It was described by Wacław Sierpinski in 1915, though similar designs appeared earlier. It starts with a solid equilateral triangle. Then you remove the central upside-down triangle, leaving 3 smaller triangles. Next, you remove the central triangles from each of those and repeat infinitely. The resulting Sierpinski triangle has a distinctive pattern of fractal triangular voids embedded within each other in a self-similar cascade. Logically, the construction relates to Pascal's triangle with its fractal patterns of binomial coefficients. And geometrically, the Sierpinski triangle has a fractional dimension around 1.58. The Sierpinski triangle elegantly demonstrates the fractal concept of infinite recursion, carving voids within voids ad infinitum to create a complex perforated whole. 2 of the most famous and dazzlingly complex fractals are the Mandelbrot and Julia sets, developed by mathematicians Benoit Mandelbrot and Gaston Julia. They are constructed by recursively iterating simple quadratic polynomial functions in the complex plane, such as EC2, CE, visualizing how the outputs diverge based on the parameter C. Tiny changes in C lead to radically different shapes, including swirling spirals, dendritic lightning bolts, and infinitely interlocking blobs, the hallmark of a fractal. Coloring each point based on the speed of divergence reveals the Mandelbrot and Julia sets in all their infinite psychedelic glory. Their endless boundaries embody mathematical chaos and strangeness. Advanced fractal properties like periodic bulbs, buds, and antennae appear. No point can decode the entire pattern. These fractals exemplify how basic recursion creates astronomical complexity, containing infinitely regressing patterns that reveal the scope of mathematical infinite. At the core of mathematically generating fractals is the use of recursion and feedback loop. Recursion means a function calls itself, so the output gets fed back as input indefinitely. This creates an infinite repetitive process where each iteration builds on the last. In fractals, the recursion happens by applying a transforming rule or function over and over. For example, in the coach snowflake, the segment dividing rule gets recursed infinite. This repetition builds exponential complexity rapidly through the feedback. Tiny changes get amplified over iterations, leading to massive changes. Recursion allows creating infinite detail from finite rules. The complexity comes not from the rule itself, but from recursively applying it within a feedback loop. This gives fractals their self-referential and scale-invariant nature. Simple programs can build fractal worlds of endless depth by leveraging the power of infinite recursion and feedback. A key feature of mathematical fractals is that their fractional dimensions accurately quantify their infinite complexity. Recall that topological dimensions describe the shape but miss nuances. A fractal line is one, but fractionally more complex. Fractal dimensions capture this in-between complexity. We can calculate dimensions using the box counting method. First, overlay the fractal with a grid of boxes of size s, count the number of boxes needed to cover the shape. Then do this for smaller box sizes, finding s for each s value. Plot this on a log-log scale. The slope gives the fractal dimension. Since fractals have infinite detail, now becomes huge even for small s. This reveals the fractional dimension value. For a line, it scales linearly, giving a dimension of 1. But for a coach snowflake, NUS scales faster, revealing its fractional dimension of approximately 1.26. Fractal dimensions mathematically characterize the limitless complexity of fractal shapes. Box counting is one method to estimate these fractional values. Our exploration today of mathematically constructed fractals reveals the underlying recursion and infinity at the heart of fractal geometry. By recursively applying simple replacement rules and feedback loops, mathematicians generate fractal shapes with unending nuanced complexity captured by fractional dimensions. Seeing these fractal sets, curves, and iterative functions helps us understand how self-similarity, scale invariance, and complexity arise from basic algorithmic processes endlessly repeated. In our next episode, we'll explore how computer graphics taps into mathematical fractals to create stunning landscapes, art, and special effects leveraging their beauty and realism. Until then, ponder infinity by zooming into the Mandelbrot set. Contemplate the emergence of complexity from simplicity by gazing at a Sierpinski triangle, and appreciate the creativity within constraints by imagining new fractal shapes.